All right, so let's move on. In a machine learning approach, we generally make the assumption that structure or pattern arises because some measurements are similar to each other. Okay, so groups of subjects, groups of samples are similar to each other. We need to discover what are these groups and how many groups are there, and also which subject, which sample belongs to which group. Okay, so which subject belongs to which group is the most common task that we're going to perform. It's also called the classification problem. What groups we have and how many groups there are, that may be given to us beforehand, such as a sample being benign or malignant. Okay, so this information may be known beforehand, and the challenge that we would need to solve in a machine learning problem is this last one, having a new sample, which group does it belong to? Okay, so this can be the problem of classification. All right. These two first questions are not always given. Sometimes we may be given a data set without any class labels. Okay. In such data sets, we can perform an exploratory analysis that tries to find patterns across data sets, across different data sets. We can group them without knowing their group labels. Okay, so even without knowing which sample is benign, which sample is malignant, we can cluster them, we can group them, and visualize these groups, and then later assign a label to them. Okay. All right. Machine learning is the study of computer systems that improve their performance through experience. Experience here refers to letting your machine learning method observe a data set, a training data set. So having been presented a training set, can they improve their performance? Okay. They do that by learning existing and known structures and rules, and also by discovering new structures within the data set. Applications involve face recognition. So when you upload your pictures, your new photos to Facebook, it automatically detects who are in those pictures. Okay, so it does face recognition. It requires you to pre-label some pictures, right? So previously you've labeled some of the faces and said, this is me, this is my friend, so and so. Taking those faces as training samples, they have trained their machine learning techniques, their machine learning methods. And now for a new face that they detect in your photo, they can automatically label it. Okay. Optical character recognition refers to scanning a page, scanning a picture, a text, and automatically determining what letters there are in that text. Okay, so when you take a picture of your check to submit it to your bank, to deposit the check to the bank using your app on your phone, they have an OCR that automatically detects who it is to, how much it is for, and so on. Okay. When you take a picture of your credit card, the numbers on the credit card are detected using an OCR algorithm. Okay. Again, these are trained on known examples. So they've accumulated pictures of numbers along with what number they are, trained their models on that. Their model has learned a way to take an image and output a single number or multiple numbers from a collection of such images. Okay. There's a vast number of applications in bioinformatics for machine learning. For example, if we have a gene, how do we know, can we figure out what that gene does? Okay. Can we detect, can we predict where it will go in the cell, or whether it will be excreted to the environment? Can we predict which other genes will it affect? Okay, so all of these are machine learning problems that we can solve using using the methods that we discuss that we will discuss in this class. We divide machine learning methods into two general classes: supervised learning and unsupervised learning. Supervised learning refers to having a class label for each sample. So if I have a sample and I know which group it is in, that's supervised learning. So I'm supervising, in a way, the machine learning method. I'm telling it, here's a sample, here's what I want you to give me for this sample. Here's another sample, here's what I want you to give me for this other sample. So that's supervised learning. Unsupervised learning is where we either don't know the class labels or we don't want to provide them, so that we want to force the machine learning method to discover groups or patterns within the data. So in this case, I would just provide all the data I have to the machine learning method and not say this one is cancer, this one is not, or not say this one is benign, this one is malignant, and let it discover patterns that are present in the data set. Okay, so that's the topic of unsupervised learning. Some examples for unsupervised learning methods are clustering. A lot of the visualization methods fall into the category of unsupervised learning. Okay. Semi-supervised learning is somewhere in between, where you would first let the method discover patterns on its own, and then you can compare the discovered patterns with the known group labels and label them afterwards. Okay, so there's a way to sort of combine the strengths of both. Okay, unsupervised learning can be useful because labeling large data sets is a very costly procedure, such as in speech recognition. Speech recognition application refers to recording your voice and using that audio and converting it to text. So detecting what you said is the topic of speech recognition. When you say, hey Siri or okay Google, there's a speech recognition, oh, sorry. There's a speech recognition that goes on behind the scenes that they've already trained to detect what you're saying. So they take that sound waves and convert it into text, okay? But that process is very costly. So going through a large collection of sound waves, a large collection of audio, and labeling them is very time consuming. So what they typically do is they cluster the data, they try to extract patterns from it. So for example, if they take a large, they take several, say, audiobooks, that's going to be our large collection of audio. We can find patterns that reflect A, patterns that reflect the sound B, and so on. So without telling it what character it is, our method can discover groups of things that are very similar to each other. And then looking at the group of A sounds, we can now label and say, okay, here's 1,000 characters that you discovered. I'm just going to call these A. All right, so it makes labeling easier. So we can run an unsupervised learning method to detect patterns and then label it afterwards. So rather than going into 1,000 entries and labeling each one as A, we can pre-cluster them and group them all together and label it once, okay? And sometimes class labels may not be known beforehand, okay? So we may not have that information at our, it may not be possible to get that information. K-nearest neighbor is another method that we can use to take large data sets and find smaller set of prototypes. Again, in the speech recognition example, we can, rather than taking all these 1,000 small samples, we can say, here's the average sample representing 1,000 similar sounds, okay? And then we can just focus on that sample sound, that summary sound, and work with that, okay? Reinforcement learning is another type of machine learning method that I'm not going to cover in this class. So in reinforcement learning, we have an agent that makes classifications, that makes decisions, and it acts on them, okay? But the result of their actions have consequences, such as a robot navigating a room. At each step, it has to decide where to go, all right? But their action changes the environment. Their action changes where they are. So they will have a reward mechanism that will tell them whether they did well or not, okay? And based on that reward, they may have to backtrack. They may have to change their idea of what is good and what is bad, all right? So that's the topic of reinforcement learning, where we have a reward signal telling the agent how well it's doing after it has made an action, okay? Or in a biomedical application, reinforcement learning could be giving a drug to a patient, right? So that's deciding which drug to give is a classification problem. Taking a large sample of, here are the drugs I gave to these patients, and here's how they reacted, here's whether it worked or not. So that data set can be used as a single classification problem, and given a new patient, I can decide which drug is most appropriate, okay? But in a reinforcement learning context, we're gonna consider the problem of, okay, here's the drug I gave to this patient, and here's how they reacted. Now tell me what I do next, okay? So we sort of have a time series of actions and their results, what next action to take. If I get the result from that, how do I change my idea of what's best for that patient, what I should do next, okay? So it's a continuing process of learning and updating your idea of what is good and what is desirable. Okay. So I showed a variation of this picture where a machine learning method is presented a data set where we would first have a pre-processing step, taking the data, putting it into a form that is appropriate for the machine learning method, such as extracting number of lines and number of curves from an image, or extracting number of words in a text. So all of that is going to be our pre-processing step. And then we will do classification. Well, I should look at the bottom first, sorry. We trained the method on a training set. And then once the method learns a rule or a set of rules or a model to make predictions, we can then present some test patterns and see how well it performs on those test patterns. Is it giving us the correct answer or not? Okay. This is the same concept displayed differently. One hypothesis that we will follow in machine learning methods is the compactness hypothesis, which says that objects that belong to the same group are similar in a feature space. So they're going to be close to each other, okay? So the benign samples and the malignant samples within themselves, they are close to each other, okay? All right. So we're going to make this assumption when we analyze the data. Depending on how we represent the data, of course, the numbers are going to be different, and the groups may not be well separated from each other. So we are going to try to create a feature space. We're going to try to extract information that separates the two sets of samples as best as possible. I'm showing some additional examples of machine learning methods here. Pattern recognition is essentially a different name for machine learning, okay? So pattern recognition, machine learning, they both try to do classification, and also visualization is also a topic of them, all right? Nowadays, you may hear the word artificial intelligence more commonly. In a purely computer science terms, artificial intelligence has a different meaning. But for most sort of popular applications, AI is used to encompass machine learning. Okay, so when you hear people using AI, they are actually using machine learning. Okay, AI traditionally, or in computer science terms, it refers to having an algorithm that solves a search problem in a way. Okay, so the machine learning is sort of a separate domain than AI, but over time they have sort of merged. And nowadays, when you hear AI, it'll encompass the methods that we discuss in this course as well. Okay. All right. So document image analysis is where we take a picture of your document, or you scan it through the scanner, and it automatically detects the letters on that page. So that's optical character recognition problem. The input pattern that we start with is a document image, and the patterns that we extract are characters or words. Document classification starts with text. The application is internet search, right? So when you type a word in Google, they have previously classified documents, and well, this is not necessarily Google, but there are some additional search engines that will do semantic categories, and they will give you more semantic information about the documents that you are utilizing. Okay. Another example of document classification is junk mail filtering. So when you go to your Gmail or your other email account, some of the emails that come into your inbox are automatically filtered into your spam folder. There's a process of categorization, classification going on behind the scenes, taking the new incoming email and deciding whether it is junk or not. That process involves having looked at a large collection of junk emails and a large collection of normal emails, building a model from them so that a new email can be categorized into junk or not. Multimedia database retrieval is where you have video clips and you categorize them into different genres, or you categorize them into different semantic groups. Speech recognition is where you say, okay, I have Android, where you say, okay, or hi Siri, and it recognizes your voice and converts it into text. That's speech recognition. Natural language processing is where you have text and you try to write programs that understand that text. So we start with sentences and we try to produce parts of speech. Which part of the sentence is verb, which is the subject, which is the noun, which is the adjective. So try to compare them and find out what is happening in the sentence. Biometric recognition is used for personal identification. So face recognition, iris recognition, fingerprint, all of these are part of the biometric recognition. In the medical diagnostic applications, we can look at microscopic images and classify them into cancers versus healthy cells. All right, some additional informations are shown below. Let's not go through them. This one is interesting. So in industrial automation, where they have different fruits going over a conveyor belt, they can have sort of a robot decide which one is apple, which one is orange, and separate them accordingly. Right? That separation will be based on a classification model that they've already trained. So they've sent through a whole bunch of apples and said, these are apples, by the way, and sent through a bunch of oranges and said, by the way, these are oranges. Their model learns using those training sets how to differentiate an apple from an orange, and they run the rest of their fruits so that the conveyor belt can separate them into different fruits or into different qualities of fruit. Wouldn't it be good to have something like this for the avocados, right? Okay. Can you detect whether avocado is ripe or overripe just by looking at this picture? Some challenges in machine learning methods are listed here. High data dimensionality is a major challenge. It's a bottleneck in some applications. So you may have a method that is sort of state of the art. Given the data, it gives you the best answer possible. It is very successful at making predictions, but it takes several months to train it, right? It's not desirable to use that method if you don't have the time to get the answer, right? High data dimensionality refers to your columns in your data set being too many. Okay? You've collected many types of information for each sample that has given you high data dimensionality. Question? What's considered high? It depends. I'd say 100 is high. 5 to 10. 5 to 10 is typically the range of applications that we look at. 5 to 10 are ideal, or that's at least the types of numbers that we see. You really need to consider the number of dimensions in relation to the number of samples you have. The more dimensions that you have, the more samples you need to learn from it. If you have just, say, the height of a person, and you try to classify that, you may need 10 people to learn a relationship between height and your target concept. But if you have measured height, weight, blood glucose levels, and 1,000 other types of information for each person, so you've collected more information, but you've actually made it more difficult for you to classify. You would now need 1 million people so that you can tease out which information is relevant and which one is not. Because as you increase the number of dimensions, the noise in those dimensions will make it look like they're relevant. So you need a lot more samples to filter them out. Some of them will be relevant just by chance if you use a smaller sample size. Okay. Another reason high data dimensionality is a challenge is in high dimensions, everything looks the same. Okay. So if you use, say, 100 dimensions and you ask, are these two samples close to each other compared to these two other samples? Because the number of dimensions is so high, the contribution of all the samples together, including their noise, will override the actual correct sort of relatedness of the samples that you have at hand. Okay. All right. So limited sample size is a related challenge to data dimensionality. The larger dimensions that you have, the more samples that you would need to collect to make sense of it. Time and memory requirements is a challenge depending on the method you use. Sometimes simpler methods are more desirable, even if we know that they don't perform as well. Memory requirement would dictate whether you can run a program on your laptop or whether you need a supercomputer that has more memory to run it. Noisy and incomplete data is a challenge because if you have incorrect samples, they will affect your model, and your model will then make incorrect predictions. Incomplete data refers to having missing data. Okay. So we may, for example, not have the gender information for a patient, or for some other patients, we may not have glucose level information. Okay. It doesn't mean that we should ignore glucose levels for everybody, but we need a way to make a prediction and utilize each sample with the amount of information that they have and utilize the information that they have as much as possible. Okay, and finally, sometimes we don't really know what we're looking for and we just hope we'll get lucky and find something, okay? Especially in the visualization methods, you would try to sort of find clusters that you can later make sense of. The curse of dimensionality is a problem that is termed to describe the problem in high dimensional spaces. And as I said, the required sample size grows exponentially with the number of dimensions. So if you have 2 dimensions versus 4 dimensions, so the number of dimensions increased by a factor of 2. Let me go from, so that's not gonna work. Let me go from 6 to 12. The number of dimensions went from doubled, right? But the number of samples I need will have to go, say 5 to the power 2. So if I had 5 samples, 5 is too small. Let's say I had 50 samples for 6-dimensional data. Now I need 50 squared samples for 12-dimensional data, okay? Which is not gonna be feasible as you increase the number of dimensions more and more. This number grows exponentially, okay? Does that make sense? So if you just look at the figure of the number of dimensions and the required ideal size of your data set, ideal number of samples, it grows like that. So if you go from, say, 100 to 101 dimensions, you would end up going from 1,000 required samples to 1,000,000 required samples. Okay? Make sense? So growing exponentially means one variable is growing way too faster than your other variable. Computational complexity is another challenge for curse of dimensionality. Most of the methods that we will look at will not do well with high dimensions. They will require a lot more time to learn a model in high dimensional data. Estimation accuracy, the accuracy of the model will also degrade with the high number of dimensions because of the noise included in each of these unrelevant attributes. The approaches to tackle curse of dimensionality, the approaches to tackle high dimensional data are listed as follows. We can extract features. We can take our data set and convert them into a new set of features. For example, we can take the height and the weight of a person and calculate a single value body mass index that captures the 2 variables into one, assuming that we are interested in the obesity level of the patient, okay? Or the weight as normalized by the height of the person is more relevant for most problems, which is why BMI would work better than just using the weight of the person. So we've taken 2 columns and converted into one. That's an advantage in terms of reducing the number of dimensions. Feature selection, which we'll cover in the later part of the course, is where we go through the attributes, where we go through the features and find out which ones are most relevant to the problem, which ones will give us the best result, and only pick those up and use them for our problem. Manifold learning and kernel learning are other more advanced techniques that we can use to tackle curse of dimensionality and represent the data in a different space. Any questions? Okay. So with the material that I covered today, you guys should be able to answer the data basics test questions. There are a few questions that there may be one or two that I did not really give the answer to. And those are included in this PDF, in this reading statistical pattern recognition and review. The first half of this paper is an overview. The second half contains some details about the methods. You don't have to focus on the details. So there are some formulas, such as for Bayesian learning. It will show you some formulas, but you don't have to focus on those. Just look at the overview, and that should be enough for this week. Okay. Yes?
Just so we can only open the quiz once.
You can open the quiz multiple times. You can submit once.
Okay, so you can save and come back.
Yes, you can. You can save your answers. So let me save my answers, and then move on to the next problem. Let me check. It says no. Okay, so I need to change that, I think. Yes, so that needs to be fixed. Okay. Where's that option? Okay, there you go. So now you should see all the questions in one page, and then save them, and then come back later and work on them again. But if you submit it, you won't be able to come back and change your answers. So saving is fine, but submitting will not allow you to change your answers later. Make sure that you submit before the deadline though. Okay. All right, so that's that. Let me repeat this.